Welcome. This is the final demo for Group 15 and our project's name is SecureScape.
This first section will be focusing on the hardware, specifically the parts, subsystems, and PCBs, which will be headed by Dylan Myers and myself, Philip Morano.
For the overview of our PCBs, we have three PCBs. We have a gadget PCB, a power PCB for the gadget, and then a final node PCB, which will have power on board.
This slide will focus on the node's parts and peripherals. The node PCB is mounted in the center section of our 3D printout. Our design will allow the LED strip to wrap around the top of the node. Our passive IR sensor will be seated in a forward-facing position so that it may pick up on movement easier. The last peripheral on the node is the buzzer, which will be placed on the backside of the rectangular section. Atop the node is our power bank, where we can easily facilitate powering the PCB and also have our wiring done internally for a more professional appearance.
For the gadget and the housing, the bottom of the housing holds the battery and the Wi-Fi router. The mid layer will hold both PCB boards and connective wiring, and the top layer will house the buttons.
This next section of our demo, we will be going through the overall functionality of our system. We will be demoing person detection and response, mobile app control, and then gadget control.
So this slide really breaks down the core workflow behind our entire project. So it works when motion is detected by our passive IR sensor, the ESP32 cam will then snap a picture and then immediately process this using our onboard edge impulse model. If that detects a person, it will then trigger the alarm and lights and then send a notification to the mobile app. The communication for this is happening over our HTTP server. It is all real-time and self-contained. We found this setup to be really fast and reliable, and it really forms the backbone of how our system responds to potential intruders.
And then just like making movement. And hopefully it comes back. There we go.
This test shows how we interact with our system through the SecureScape mobile app. When the user taps the button, whether to restart the system, turn on the alarm, or toggle the lights, that command is then sent to our central gadget over HTTP. The gadget then forwards it to the node, which performs the requested action. The app even gives you feedback once the command goes through. In the demo that follows, you'll notice some error messages. Those are not really true error messages, but just instead timeout responses from the delay of our HTTP server. As you'll see in the video, everything functions as intended with minimal delay. Just a heads up, the next couple of tests do use the buzzer sound, which can be pretty loud and like kind of piercing, so we recommend lowering your volume in advance. This test focuses on using the SecureScape gadget directly. So when a switch is flipped on the gadget, it will instantly send a command to the correct node, no app required. From this, the node will then carry out the action, like toggling the alarm or the lights, and again, as you'll notice in this demo, there's some slightly noticeable delay within the triggers. This again goes back to our HTTP server introducing some extra responsiveness and lag into our calls. However, everything still functioned as intended as in the video.
Alarm on.
I would say schematic just for your PCBs.
Alarm off.
So like even those stuff too.
Are they on the schematic?
Lights on.
Well, because like it would be like the whole schematic.
Lights off.
Not just the schematic of the button. So like if the schematic of the button is on, your schematic is tied to the
Should work, it's just the way.
Okay, there we go.
Now getting into our engineering specs demo.
In the following slides, we will be demonstrating our system's detection accuracy, response time, and detection range. To detect accurately and for fast response times, we need reliable communication across our devices. Detection range is mainly a hardware limitation of the passive IR sensor, but even when movement is detected, our system must reliably react within a minimum of 5 feet away.
So like it responds well, it's just
The main purpose of these tests is really just to verify full functionality of our complete system from start to finish, from motion detection to our app notification, with different test subjects, as you'll see in the following clips.
well yeah, that's still fine, but
Okay.
keep it. So hopefully it picks up on it. Yeah. Just trying to move it back and hopefully. then just like making movement. And hopefully it comes back. There we go.
The results from our detection accuracy demo were quite impressive. We achieved an 80% detection rate across 10 test runs and observed that detection accuracy decreased as we moved further away from the camera. While person detection remained consistent, delays in data transfer due to HTTP affected mobile notifications, contributing to less than 100% functionality rate. Our results established a strong baseline, and we have identified key areas for improvement, including refining detection range and optimizing data transmission for more reliable and faster notifications.
This test is measuring the response time of our system, from motion detection to the receival of the notification. To get a more reflective timing of real-world scenarios, we're starting the timer when the person detected flag clears as shown by the all clear on the top of the screen, and stopping when the alert fully covers the dashboard.
Just hoping that. There we go. And then just like making movement. And hopefully it comes back. There we go.
The response time varies within quite a large margin. We've concluded that the delays are most likely due to network latency within our HTTP communication between the ESP32 CAN board through the router and populating images on the app. Another potential bottleneck would be the lack of memory in our microcontrollers. We understand that response time is paramount in every real-time system, and we're focused on improving this aspect of our project.
To test our detection range, we started at a distance where the node couldn't detect a person and slowly moved closer until a detection notification was received on the phone, as well as a slight beep you can hear from our alarm in the videos. Since detection was consistently accurate around 15 feet, we extended our testing range to approximately 25 feet to better evaluate its limits.
Oh,
Detecting me anyway.
is this recording from? Okay.
So with our finalized system, we're definitely able to consistently detect people with a range of roughly 3 to 20 feet, with an average range of about like 12 feet. All of our baseline tests from previously have passed, confirming that we do have a reliable detection within our desired range as shown in that table. To explain the asterisk applied on the 2-foot baseline test, it really just marks a specific occurrence in our test where when a person is too close and blocks most of the frame, detection occasionally will fail due to lack of what our image processing model would interpret as a human. But we also just observed some slight delays with our peripherals, most likely just caused by HTTP response lag and overwhelming of the server with the PIR sensor, but overall our functionality was great and exceeded our standards. We appreciate you guys tuning into our final demo. Big thank you from our team.